Welcome back, students. We already covered most of the important topics in polar coordinate system in the previous video. Here in this video, let's have some fun. We're going to spend some time on curves given by polar coordinate systems, or parametrization, which we call polar curves or parametric curves respectively. We're going to have some animations too, lots of it actually. But before that, we need just a little bit of review. Here's a visualization of the definition of the polar coordinate system. It's a scheme that represents a point and a plane by two quantities. The direction, which is measured by the polar angle depicted in red in this picture, and the distance from the origin to the point that you're interested in that direction, which we call the polar radius, which is depicted in blue in this visualization here. The angle, of course, is periodic. Adding or subtracting any multiple of 2 pi will not change any direction. So the periodic behavior, the ambiguous behavior, is inherent in polar coordinate expression. But there's more to it. The polar radius can take negative value too, and consequently you take the direction and go backward. What do I mean by that? I'm talking about something like this. This is a situation where the polar radius is positive, so it's the same as the physical radius, physical distance. No problem there. On the other hand, the polar radius can be negative. Here in this visualization, theta is between 3 pi over 2 and 2 pi, so we have to move toward the fourth quadrant. However, r is negative, so we have to move backward and we end up with in the second quadrant. That's what the negative polar radius do. And that's summarized here. In other words, changing r to negative r is equivalent to changing theta to theta plus pi. If you do both, then you just come back to the original. Changing r to negative r is taking a direction and going backward. Changing theta to theta plus pi is taking a direction and then take the opposite direction and then move forward. Do we end up with the same thing? Just moving backward, or turn around and move forward? They're the same thing. Now let's move on to the convergent formulae. And polar to rectangular is simple. X is r cosine of theta, y is r sine of theta. Rectangular to polar, on the other hand, is a little bit harder because of the ambiguity we just talked about. My favorite scheme is this. Keep r positive, square root of x squared plus y squared by Pythagorean theorem, and adjust the polar angle appropriately. Take arctangent of y over x if you point in the first or fourth quadrant. In that case, arctangent of y over x will cover, because arctangent takes values between negative pi over 2 to positive pi over 2. But it will not cover second and third quadrant. In that case, you have to add pi. Another way to do that is to keep the polar angle as arctangent, but if necessary, change r to negative value, but I don't like it very much. And also, the formula is a little bit more useful for complex numbers and other applications. Okay, let's move on to the real topic that we have to discuss. Curves given by polar coordinate. Let's discuss some curves given by r equals f of theta. Well, here's the simplest example. R is given by sine of k theta, where k is various values. When k is equal to 0, then, well, sine of 0 theta, so it's 0. R is always 0. In other words, we just have a dot. Well, that's not really interesting, but let me show you. No matter what direction I take, the red point is, well, staying at the origin because r is always 0. But when I take different k value, things are a little bit different here. In this case, k value is 1. So, well, let's see what you have here. R is sine of k theta, so r is equal to sine of 1 theta. When theta is between 0 and pi, as you just saw, then sine value is positive. In other words, r is positive. What do I have? The red point is pointing toward the gray arrow. However, when theta is between pi and 2 pi, in other words, the gray arrow is pointing toward the third or fourth quadrant, lower half plane. The red point is pointing the other direction because sine is negative there, r is negative. Consequently, we have this kind of behavior. Now, when k is 2, as you see in this picture, in this case, let's see, sine of 2 theta is positive when theta is between 0 and 2 pi, 0 and pi over 2, excuse me. In the first quadrant, it is positive, and also between pi and 3 pi over 2. So in third quadrant, positive r value. As you can see, the red point is following the gray arrow in the first and third quadrant. However, in second and fourth quadrant, when theta is between pi over 2 and pi, or 3 pi over 2 and 2 pi, then sine of 2 theta is negative. In other words, r is negative. Consequently, this red point is pointing the opposite side of this gray arrow. This is when k is 3, r equal to sine of 3 theta. K is 4, and that's k is 5. Okay, somehow these are called roses. They look more like chrysanthemum to me, but traditionally they are called roses. Now this kind of curves are called Limassons, and is given by r equals a cosine of theta, as you see here. The simplest case, when a is 0, then we just have a circle, because a is 0, so a cosine of theta is 0, so we just have r is equal to 1. The distance from the origin is constantly 1. What do you get? We have a unit circle. Not very interesting? Okay, let's change a value into 1. And this situation is called cardioid. Kind of looks like a heart. That's why it is called cardioid. Now, a value is 1. So we have r is 1 plus cosine of theta. Now cosine of theta reaches maximum at theta equal to 0. That's when cosine of 0 is 1. So r value reaches a maximum 2. That's when the theta is 0. In other words, we are pointing toward the polar axis. If you move toward the right hand side, that's the maximum r. That's the maximum distance away from the origin. Now if you point toward, say, vertically up, when theta is pi over 2, then cosine of pi over 2 is 0, so r is 1 plus 0, so we have r equals to 1. So distance from the origin to the point that is crossing the y-axis, or y-intercept, is 1. Now if you point toward the left-hand side, when theta is equal to pi, then we have cosine of pi, that's negative, so we have 1 minus 1, r equals to 0. What do you mean by that? This red point comes back to the origin when the gray arrow is pointing toward the left-hand side. Toward the left-hand side, that's when theta value is pi. Now if I change my a value around, when a is a little bit greater than 1, then this a cosine of theta part can become greater than 1 because we are multiplying some number a greater than 1. Consequently, r value can become negative depending upon theta value, especially when theta is pretty close to pi. Consequently, we have this inner loop given by negative r value when the red dot is pointed to the other side, pointed backward, compared with this gray arrow. Well, if I change a value just continuously around, then as you can see, the curve is changing according to the a values. And then, of course, the dot is moving around, the arrow is moving around according to theta. Okay, enough fun for that. And in this situation, with r equals a cosine of k theta, and theta value changes, A value changes, and let's see what happens here. K is 0, so this A cosine of K theta part doesn't really contribute too much. When K is equal to 1, then we have the same as the Cardioid case, or Limassol case actually, a little bit more general. When K is equal to 2, even more interesting. And K is 3, well, still more interesting, or just the same? Anyway, it's an interesting situation. By the way, change of theta moves around the red point and gray arrow, and change of A moves the curve itself, the blue curve itself around, change the shape of the curve. Change in K, of course, affects both of them. Still different K value. Still different K value. We have another K value. Okay, enough fun. The next picture is coming from the textbook, and this picture reminds me of flowers, so I usually call it flower, and aesthetically it's beautiful. I think that's why our textbook author brought this one, the textbook. And the next picture is actually generated, at least in part, by one of my students, Maria Mancera, several years ago, and I gave her a mathematical program to play around, and she changed parameter here and there and got a picture very similar to this, and I liked it, so I changed a little bit further and created and adopted into my notebook. Looks like a butterfly, isn't it? Okay, those kind of things are examples of polar curves. Curves given by r equals to a function of theta. Now, in general, we can go beyond polar coordinate system and consider even more general type of picture. Because in polar coordinate, x is r cosine of t, y is r sine of t. But then again, if we do away with that restriction of r cosine of t, r sine of t, and consider x as arbitrary function of t, and y as arbitrary function of t, then you're going to get really arbitrary curve. Oops. And here are a couple of examples. Oh, come on. This one has nothing to do with polar coordinate system, because x is not given by r cosine of t, y is not given by r sine of t. However, both x and y are periodic. They consist of sine and cosine. We have periodic behavior, kind of like that. This kind of thing is called parametric curves. Both x and y are functions of t, and it is a curve given by moving particle model. X comma y can be considered as horizontal and vertical position of this red particle, and t is time. So as time changes, the particle moves around, and the trace of that is the curve. And here's another kind of curve. In this case, not periodic, because we have sine and cosine, yes, but also we have 2t and t part. This part and that part are not periodic. So as you can see, we do not have closed curve. And this example is an example of something called cycloid. And it's an important example, both in physics and engineering. And it represents a trace of moving point, that red dot, on a rolling circle. And each arch is pi t is moving from 0 to 2 pi, 2 pi to 4 pi, 4 pi to 6 pi. Those gonna be arches. And this class, the cycloids, are associated to some historically important problems like brachistochrone problems or things like those. And there are good explanations written in our textbook, so please go ahead.